the other, right? Suppose we have a P1 process currently running, and from P1 processor has to go to process P2. Okay, so in that situation, first thing is we have to save the context of CPU. That means we have to save the register variables or CPU register variables values and all those things. That is the first thing. Okay, then the program counter values are saved. Okay, second step says that update the PCB of which process. So we need to update the PCB of the process which is currently in running state, right? Why? Because now that process will move to another queue. Okay, so what are the possible queues where the process can go from running state? Yes, which are the possible states? It can go to blocked. Yes, because it may happen due to event wait. Yes, ready, as well as ready suspend. Yes, good. Actually, the answer is there on the third step. Yes, exactly. Right. So after we have saved everything, right? We have saved the PCB, we have saved the CPU register values and everything. We can actually move the PCB to appropriate queue. But we don't actually move the PCB, right? What do we move? Just the pointer. Remember, we maintain only pointer. Yes, right? So the pointer is actually set to appropriate queue. Okay, that is what happens, right, in background. So now we are done with the currently running process. Okay, next step is to pick up a new process, right? So step number 4 is selection of another process for execution. Now, who will do this? Who will select the other process? All of you know that, right? Yes, we call it dispatcher or scheduler. Yes, exactly. You can name it as that. And what is the process ID of that? Can we just recall? Process ID of dispatcher in Unix? Very good. It is 0. Read, it is 0. 1 is for init. Yes, remember that? Init is parent of all, right? Yes, yes. So selection of another process, that is step number 4. Step number 5 is update the PCB of selected process. Now it is possible that that process also ran for some time, right? It got its chance, and when the timeout occurred, it went back to ready state, right? If that is the situation, then the PCB of that process has to be retrieved, and we need to restore that context. Are you able to understand this word, restoring the context of that process, right? Restoring the context includes what? Can you tell me? When I say that you have to restore the context of selected process, what are the things involved? Yes, CPU variables. Load it in the memory. Very good. Pointers have to be set. Very nice. Right? So that happens in step number 5, 6, and 7. Step number 5 does what? It just fetches the PCB. It examines the values which are there in the PCB, like process state and all those things. Fine. Actually, in step number 5, do we need to change process state? What do you think? Do we need to change process state? What is the answer? Yes or no? Think and answer. We have selected that process for execution. So do we need to change the state? Yes, that is the answer. True. What will be the state? What will be the state? That is my next question. Running. Exactly. Very good. Right? So that happens in step number 5. Right? Update the state information. Okay? Pointers will be pointing to appropriate location in step number 6. Pointers will be pointing to appropriate location. Which pointers? Program counters, stack pointers, memory pointers, right? That happens in step number 6. Okay. Step number 7 is going to restore the CPU variables, CPU register variables. Okay. So whatever variables earlier, whatever values they were holding, right? They will be reflected on the CPU. right? So if the values of variables were 5 and 6 earlier, so those 5 and 6 values will be restored in the CPU registers. Are you clear up to this? Step number 7 now. I could sense that there was some confusion last time, so that's why I've taken a revision, right? Good, good. So this is what happens whenever the process switches. Now tell me one important question that can be asked as an objective or that can be asked as a theory question is process switch. If I give you a statement, let us say process switching takes more time than mode switching. True or false? Process switching takes more time than mode switching. Mode switching means we switch from user mode to kernel mode, right? While process switching means you are taking out one process entirely and bringing another process. So think and answer. Process switching takes more time or it is more time consuming, more effort consuming than mode switching. Yes, Anish has answered. What about others? Okay, Jenny has answered. What about others? I can see 97 people, right? Don't worry if it is wrong, right? Okay, Keval is saying false. Shail is saying true. Okay, I'm getting multiple answers as true. Yes. Okay, so I'll just go in detail, right? When we switch the mode, if you remember, when mode switch occurs, what we need to do just, how you will come to know that mode switch has occurred? We have a bit, right? Remember that? Yes, right? And what is that, where that bit belongs? It belongs to a data structure called program status word, PSW. Yes, exactly. So only thing that happens is you just change that bit, okay, and then the kernel function gets executed. Kernel functions, let us say if you are calling open system call or read system call, right, that gets executed. So do you think that is costly operation, just changing the bit and calling the kernel function? It is not. And that is why the statement I said is true, because see, in this situation we are executing 7 steps. Are you getting the complexity? Yes or no? In process switching, we are executing 7 steps, while over there it is just 2 to 3 steps, not more than that. Okay, that is why it is said that process switching takes more time than mode switch. This is a common question. You will face this in the exams like GATE, even, or even in the exams of placement, right? This is a very common question in operating system. So please remember this, right? In reverse, it can also be asked, that is, mode switch is less costlier than process switch. True or false? Mode switch is less costlier than process switching. True again. All of you are clear? Yes. Good to see the answers. Yes, right? So, remember this point, right? At least till you face your interviews, right? Because this is a common question being asked, right? Now, the next topic is how OS is actually working inside your system, right? How OS works inside any computer system, right? So, for that, we need to answer one more question. Is OS itself a process? What do you think? If OS itself a process? The answer should be yes, definitely, right? But we can say it is a complex process, right? I hope you agree. It is a complex process, right? So the question is this. Let us read that. If the OS is just a collection of programs, right? That is the first thing. If it is a collection of programs, and if it is executed by the CPU, like any normal program, right? Is OS a process, right? And the answer, as we know, ideally should be yes, right? But still, there are many other models which were designed earlier, right? So we are going to look at those models, how actually OS was designed and how it executed. Okay. So if the answer is yes, that is, if OS is a process, then how it controls, how it is controlled. Okay, that is going to be again interesting. So we have three models for this. Right? We have three models for this. Just observe this figure. I'm going to take up each topic one by one. Okay, I'm giving you 1 minute. Try to observe and understand the difference. Okay, in the first figure, you have number of user processes executing on the top of kernel. That means OS is not acting as a process over here. OS is a separate entity. Are you able to understand that much? By looking at the first figure, OS is acting as a separate independent entity, right? While on the top of that, you have user processes, right? So that was actually older design of your operating system, right? That was older design because whenever you want to invoke some OS functionality, you need to go through a complex path, right? Whenever you want to invoke some OS functionality, which is very often required a complex path to be taken, right? So that was the earlier model in the first figure, what you can see. Can you tell me what happens in the second? Can you summarize in short? This is what actually we have in our computer systems. The second model is a popular design by far, and it is a standard operating system design in small scale PCs, or that is what we have currently, right? Integrated, yes, good point. Anyone else? Every function needed at present in process itself, yes, very good. OS acts as a root process, okay. PI is a child of OS. Yeah, so what you can observe over here is you have a number of user processes, but OS executes in the space of user process. Listen to my statement carefully. OS executes in the space of user process. Is that understood? Right? Yes, sure. OS functions execute as a part of user process only. That means mode switch will occur over here, but process switching will not take place. Right? See, in earlier model, what was happening? The OS was lying separately, while over here, processes are containing the OS functionalities, right? So there is a, you can say, there is an overhead over here. That means your system has to maintain n OS images, n OS images, right? Are you understanding this statement? Your system has to maintain n OS images, right? What do you mean by n over here? N is number of processes. Yes, n is number of processes. Exactly, right? So in this situation, whenever OS function wants to execute, let us say you are calling an open system call or read system call, only mode switch will take place. Only mode switch will take place because now you will enter the OS area, right? Although it is part of the user process, right? But only mode switch will take place. Right now, just remember this. Don't worry if you are getting confused. We will see this in detail. As I said, this is just the introduction slide, right? Remember one point. In this case, only mode switch takes place. Yes, it can be hectic, but nowadays we have good CPUs and better capability, so that's why it is not hectic. Is it? So that's why I said this is the most popular approach, right? Yes, as a human, if we think, if we think, it can be difficult, but if you have a capable hardware, it can be managed. Yes, OS reunit. What do you want to say, Jenny? Where is it mentioned? OS functions. It is OS functions. I think it is not clearly visible, but I will go to the next slide where it is clearly visible. Right? Yes. Okay, now look at the third figure and try to find out the difference between second and third. And tell me, what do you observe? Second and third. Just give me the differentiating points of third, which is there. Reusability of function, okay. That is one observation. OS functions execute separately. Yes, OS runs as a process. Very good. OS runs as a set of processes. That's what I can add to this. All of you can observe this. User processes are running separately while OS is also running as a set of processes. Getting this idea? Yes or no? Okay. Okay, I'm getting at least 2 yes, right? Now, I'm going to the next question. Do we need process switch in this situation if you want to execute OS functions? Is process switching required? I'm repeating the question. In third situation. Yes, that's correct. Why? Can anyone give me the answer? Why process switching is required? Because OS is actually behaving as a process. Exactly. So can it be costly? You just proved that, right? And that is why this model is not commonly used, right? You can say if you have a high-end servers, right, in that situation, or if you have a distributed operating system. Yesterday also, I had a question from, I think, someone, right? Preet, I think you asked that question. So when you have a distributed OS kind of mechanism, right, in that situation, this model will be suitable because in that situation, the cost can be reduced, right, because your hardware is capable. While over here in normal CPU, if you have a single CPU machine, can we go with this model? OS as a process? No, right? Because it can be costly. So in summary, what we can say, which is the ideal model to follow? Although the details are coming up, but which is the ideal model to follow according to you? 1, 2, or 3? It is second. It is second because over there we only require mode switching. Right? Because OS functions are part of the user space only. That's why we don't need to switch processes to execute OS. Right? So that's why I told you in the personal computers which we are having, the second model is being used. Right? Yes, I have one question. I think yes, this needs multiple CPU. So Sainish, yes, ideally you should go for a distributed operating system for the third model, right? So in distributed OS, generally you have multiple computers, right, where the OS gets distributed, right? So that is the general case, right? Clear? But not compulsorily, right? If your single machine's hardware is capable, then also this model is usable, right? Yes, right. Okay, so now I'm going for the detail. Right? Now it will be easier because we have seen the basics. So the first model which we saw is called non-process kernel. Non-process kernel means kernel is not acting as a process. It is acting as a separate entity. That's why it is called a non-process kernel concept. Okay. So kernel always executes outside of any process. It is totally a separate entity. Fine. And whenever kernel functionalities are executing, right, you can say that your system is currently running in privilege mode, right? And we call that as a kernel mode actually. But in earlier system, that term was not introduced. So that's why it was called just as a privilege mode. Clear with this model at least? Yes. Kernel is a separate entity while processes are separate. Okay. Now what should happen whenever process calls some kernel functionality, right? That we'll see. Okay. So understand the first line. When currently running process is interrupted, okay, or it issues a supervisor call, right? Supervisor call is nothing but when user is requesting some OS function, right? As we have seen last time. And interrupt, right? What will happen in this situation? Context of the process, let us say if it is P1, will be saved and the control will pass to the kernel. Okay, so actually we are not switching the mode over here. The concept of mode switching was not introduced when this kind of system was designed. It was called control passing mechanism. Are you able to understand this line? Yes or no? Whenever interrupt or supervisor call happened, that means whenever you wanted to execute kernel part, only the control passing was happening, right? From user area, you are passing the kernel control to the kernel area. That was the mechanism, right? And you can say mode switching, yes, Keval, but that term was not introduced in that era, right? So that's why I'm not saying that term. It was called control passing, right? Yes, yes. So when this kind of system is there, kernel, or you can say the OS, is given a separate stack as well as separate memory. I hope you agree to this, yes or no? Because if you are assigning a separate area to the kernel, it should be given separate memory and separate stack, yes or no? Because if you mix that with the user process, then again you can say that the privilege mode will be violated. Privilege mode will be violated, right? So that's why kernel area was given a separate memory as well as separate stack. Nothing was shared, right? Nothing was shared with the user process. And that is why it is called non-process kernel. I think now you can get the name, right? It is out of the process. That's why it is called non-process kernel. Okay. And as I said, this approach was used by older operating system where we were having only limited amount of process switching or limited amount of processing requirements. Right? In that kind of model, this was suitable. Right? So now it is no longer suitable because we have number of processes as well as the size of OS has increased. Right? So that's why it is going to be difficult to manage in current situation. Right? Clear with this first part, non-process kernel? This is the first model, right? As I said. Now let us look at the popular model. Second model is called execution within user process. Right? That means your OS functionalities are part of your user processes and they execute also within the user process. That's why it is called execution within user process. Right? No need of process switch to run the OS routine. Agree to this? We already discussed this, right? Yes. Now observe the right hand side figure. Right? It is process image. Okay, can you all hear me once again? Yes, yes. Sorry for the interruption. The internet was lost. Yes. Okay, so we'll continue. Okay. Is the screen share visible? Yes, yes. Okay, okay, fine. So we were discussing about the right-hand side figure. Initial part of your process image is the PCB, right? And then we know it contains code, stack, and everything, right? So we have a user stack. The first gray block is for user stack. Then you have user address space where the program and data will be stored, right? That is second gray block. Okay. And now, as OS is executing as a part of your process, right? So we need to allocate space for kernel stack also. Yes or no? Space for kernel, because whenever the OS functions will execute, right, it will also require space for storing its variables and everything, right? So that's why a separate kernel stack is allocated within user process. Understand this, within user process, right? So yes, we can say that we require more memory, but nowadays memory is not an issue, right? So that's why this is a suitable design. Okay. And then you may have a shared address space, right, where the kernel can store some parameters which can be even accessed by the user. A dashed part at the bottom is such area where the shared area is allocated. See with this model, yes. Whenever we execute within the user process, this is the model we follow, right? I'll be uploading the slides. Should I repeat if you are not clear? Yes, yes, sure. So, Urjit, let me directly say that whenever we use a normal process, right, we have data and stack, yes or no, for each process, plus PCB, okay? That is what forms the process image. Clear? That much? Yes. Now, if OS functionalities within, right? So that means you will have to store your own parameters while the kernel function is executing. Yes or no? For parameter storage, right? So for that, we are allocating separate space inside the process only. That is called kernel stack. Okay. And then comes shared address space where shared variables or shared resources, right, between process and kernel can be stored if required. Yeah, so that means it is not. Are you able to understand this now? Right? If required, this last area can be allocated. Right? Yes, but up to kernel stack is compulsory. Right? That is the design. Okay? Fine, good. So now let us see the details, right? As I said, OS works as a collection of routines within user processes, right? And this is and workstations, right? Small scale workstations. Okay. Separate kernel stack is given to each process while it is in kernel mode. It will only be used when it is in kernel mode, right? Other than that, that area won't be touched upon, right? When in call happens, right? What will happen? Just mode switch or process switch or both? What do you think? In this situation, only mode switch will take place. In both. So Ronak, in this situation, OS is not acting as a process, right? So that's why we don't have to switch processes, right? Yes, if you are going from process P1 to process P2, in that case, your answer is correct, right? If you are going from process P1 to process P2, that means process switch will be required, right? Only process P1 wants to execute OS function. You can say it as a control switch. Yes, according to older notation, you can say Urjit, control switch. Design mode switch was introduced. That term, mode switch, right? Actually, right? But as design different names, yes. Right now, in this, that is, we should say mode switch, right? Create word. Okay, so when interrupt or supervisor call happens, it's in kernel mode, right? That means you will set the bit in PSW. Control is passed to the OS, right? Because now kernel functionalities, control is passed to the, but the OS functions will take place in process only. That is in this area, which you can see on the right hand side. Okay, so that is why we say that required. Okay? No process. Fine, and I hope you can see the benefits over here as well, right? We just have to do mode switching. Cost of maintaining n process images, right? But if you have capable hardware, that is easier to manage. And newer operating systems are using this concept. I'm going for the third one, process-based OS. Right. As I said, this can be used in a distributed operating system design or in a high-end servers, right? Because in that case, OS clicks, right? It has to be complex manner, right? So in this case, OS is actually divided, right? And from software engineering, you remember what is the benefit of dividing a system into modules as a single module? Anyone recall and tell me? Managing the load, yes, perfect. Easily manage the system, right? If you are distributing the work, okay? So that is the benefit we can get in this model. Single point failure, exactly. If your OS is distributed on number of machines, then this is correct. So we implement OS as a collection of system, right? Collection of system processes. This kind of model will involve process switching, right? As we discussed, operation, right? So you need enough memory. This kind of. Now, I think you observed one more thing layer we have in this previous model is process switching functions. So what is that? Can you tell me? Process switching functions. That part is actually shared across all the processes. This is the meaning of saying. Can anyone tell me what do you mean by process switching functions? That is not. You are studying an entire chapter on that, right? It is dispatcher. Yes, exactly. It is the scheduler which is going to be shared, definitely, right? Because scheduler will not be private to any process. That's why process switching functionalities or your dispatching code and whatever other code that is common at the bottom have that one. Okay. So are we clear of OS actual design, right? How it is actually, right? So either OS can execute as a separate set of processes, that is the first design, execute as as you can say as a part of user processes. And that is second. Third design says that OS executes as a set of different processes, right? Depending upon the requirements, the designers go with any of this model. But as I said, the second one is the most popular. Okay. Preet has a question: how OS executes in virtual machine on top of our host OS, hypervisor and other stuff? How things work in case of virtual machine? Yes. So in that case, actually, Preet, it is acting as a process, right? That virtual machine is a process. Inside that process, your OS is getting executed. That is the mechanism, right? So, because see, generally we can't run anything until and unless it is a process, right? So your virtual machine is acting as a OS. Not exactly Urjit, because process-based OS says that your OS functionalities are divided. Functionalities are not divided. OS encapsulated inside VirtualBox, you can say, right? So it's running with the second model, right? Itself. Yes. So now we'll discuss the security issues, right? So what kind of security issues we can face when we are having operating system? Learning this all concepts in sixth semester in one of the subject called NIS, Information Security, but I'll give you basic idea how OS can be protected against, right? And what are the risks that we need to face? Ideally, which access should be protected? Not be allowed to access. What the users should not be allowed to access. Yes. That means root access, right? We should prevent users from gaining the root access, right? There are different types of attackers, right? Which may try to attack your system, right? So this is just a small topic which we'll cover before we go with the 9-state diagram. So yes, exactly. Security issue can occur. Yes, that's correct, Preet. Right? So there are two types of risks that your system can come across. First is intruders, and the second is malicious software, which we know as a malware, right? In intruders, there are three categories. First category is someone, right, who is called masquerader, right? So they're basically someone who is outsider but still, right, by gaining the privileges somehow. Called unauthorized access from an outsider. Okay, misfeasor is someone who is insider, but gain the supervisory privileges. That means who tries to access the restricted aspect. Not allowed to access that area, but you access. That is called insider who is penetrating your system. Seen user, right? Who can be outsider or insider. Outsider or insider, right? There's a slight mistake over here. Gaining the supervisory control. And what is supervisory control? Supervisory control. Root access, right? If either the outsider or insider is getting the supervisory the access. Yes. Right? Later on. Right? So, right, that is a taker. There's of preventive, we will be studying those in next, right? Of course, so my two parasitic needs, it will always take behavior. Yes or no? And this or the soft running when I lost. Yes, I lost the connection once again. So let us resume. Okay. So we were discussing about security threats and different types of security. I hope you got the basic idea. Yes, what kind of intruders can be and what kind of softwares that can hamper your OS. Yes or no? This is just a small topic, right, which is covered as a part of your OS. Yes. Yes. Good. Okay. Okay. Good. Thank you. So now I'm going towards the 9-state diagram, which is actually I wanted to discuss in detail. We'll take 15 minutes or so, and then I'll pass it on to AKG sir, who will take up the AA class, right? So in case of Unix, right, if you read this first term, it is called Unix SVR4. Roman term, it is System 5, Release 4, right? So we are going to discuss this Unix versions diagram. It involves total 9 states, okay, and it uses the second model which we studied. Right? Second model means where OS functions execute as a part of processes. Right? OS functions execute as a part of processes. Right. So unless you remain in the same process, that means when the same process wants to execute the kernel functions, which kind of switching is required? When the same process, let us say P1, wants to execute kernel functionalities, is required only mode switch. That's correct, right? But when the OS gives control to another process, From T1, it goes to the other process. Which kind of switching will be required in that situation? Due to timeout or due to, let us say, interrupt or priority, then process switching will take place, right? So process switching does not occur actually while executing OS functionality. That is the essence I wanted to clear, right? With that knowledge, now we can go into this, right? So there are two kinds of processes that this system uses, right? Generally, the user processes execute in the user space, and whenever required, mode will be switched. Mode will be switched, right? And while you are running in the kernel mode, the system says that you are actually running a system process while you are in kernel mode. Right? Then again, the control will be back to user process, right? It will be clear when we'll see the diagram. So this is the diagram. Just observe it for 1 or 2 minutes. Then we'll go with the states, right? I will not be discussing all the transitions over here, right? Because now we have had enough discussion on that. Most of them are already there. Only what is not covered that we'll see, right? Which are the new states? Can you name them? Zombie, yes. And we have seen that in lab, right? You know what is a zombie state? Preempted. Yes, that is a new state. Okay, let us start with the first one, created. What is created state? It is equivalent to which state? New, exactly. New, very good. In memory, which is that state? Ready to run in memory? Diagram, right? Not 6 state, 7 state diagram. Yes, ready state. Ready to run swapped, which is that? Ready to run swapped. Ready suspend, very good. Right. Sleeping or asleep in memory, which is that? Asleep in memory or sleeping, there are two names. It is block state, yes. We are still in main memory, right? Sleep and sweat, which is that state? Block suspend, very good, very nice, right? Now, actually running state is divided in two separate states over here, right? Because we are following this model, right? We are following this model, right? Where OS is running as a part of your process, okay? So whenever you are running the kernel functionalities or OS functionalities, which will be your state? Can you tell me from the figure? Whenever you are running OS functionality or system calls, at that point, what will be your state? Kernel running. Exactly. Yes, that's true. Right? And whenever you are running just user part of the process, right, which is not involving OS functions, which is that state going to be? User running. Exactly. So got the difference? Understood? Right? Whenever OS functionality will be called, right, at that point, user running to kernel running transition will take place. And you can see the, I think you can read that, right? System call or interrupt that will switch from user running to kernel running, right? Can you read that on the screen? Yes, and on return, you will again go back to kernel, right? Now there is one new thing over here. You can see preempt. Now I covered that term earlier. Do you remember what is preemption? When you say that your OS preempts one process, what happens actually? Preemption means, if you remember, I told you, taking CPU away. Exactly, it is process switching, right? Taking CPU away from one process and giving it to the other. Remember that definition? Yes, right? So that is called preemption. Okay, so this transition says that the process was executing in kernel area. The process was executing in kernel area, and it finished the execution of kernel. Understand my statement? Process was executing in kernel space or in the OS area, and it finished with the execution. While returning, while the return path was taken, preemption occurs, right? This may be due to priority, this may be due to any other reasons that we have seen earlier, right? In that situation, that process, which is from which we will take away the CPU, will enter preempted state. Will enter preempted state. And I'm going to repeat it once again. While it was executing in kernel, everything was fine, right? But when it was returning through this return arrow, in between process switching had taken place, right? In between, okay? So in that spatial scenario, Unix has designed a separate state that is called preempted. While returning from kernel mode to user mode, if the process is preempted, it will enter preempted state. Clear with the definition? I hope you can follow the transition also, right? And from preempted, once again, it can go to user space, right? Once its chance comes back. Once its chance comes back, right? Clear with that triangular transition? No preempt. While it is running in kernel mode, it won't be preempted, right? Because it is a privileged mode, right? Yes. But while returning to user mode, it can be preempted. Got the point? I think all of you are clear with this, right? Yes. Sure. Signing. See, one basic reason is preemption on priority. I hope you remember that reason when we discussed this transition in the seventh state diagram. Preemption can occur when a lower priority process is running and a higher priority process joins the ready queue. In that case, definitely the chance will be given to the higher priority process. Yes. So the CPU will be taken away from the lower priority process and then it will be given to the higher priority process, right? That is one reason, right? And then there can be many other reasons. Priority is just one reason for this. Right? Clear? Yes, right. So now I'm giving you this diagram. Just read it once. I'll also read with you. And I hope you both can understand, right, in detail. So these are the 9 states which is mentioned, right? User running, that means process executing in user mode. Okay. Kernel running, that means it is executing in kernel mode. Okay, so only mode switch has taken place, not process switch. Switching and preemption is same. So actually, Sainish, when preemption occurs, after that switching will take place. Preemption means you take away CPU, right? And switching means you are giving that CPU to another process. I hope you are following this, right? So this is a chain process. After preemption takes place, switching will occur, right? Yes. Okay. Third, ready to run in main memory. You know that it is ready to run as soon as kernel schedules is. Generally, we write it kernel, but it is called dispatcher, right? Because dispatcher is a part of your kernel, right? Asleep in memory, unable to execute until event occurs. So waiting for an event, right? It is in main memory. Okay. Ready to run swapped. It is ready to execute, but due to lack of space, right, it is not moved in the main memory. Swapper, another name of dispatcher, right? You got one more name. Yes or no? Swapper, dispatcher, right? Scheduler, all are same, right? Swapper must swap the process into main memory before the kernel can schedule it. Okay. Sleeping swapped, right? We know that it is blocked, but it is in secondary memory. Okay. Preempted, focus on this. Process is returning from kernel mode to user mode, but kernel preempts it and does the process switch. Sinish, I think now you can be clear with the question, right? Kernel first preempts and then process switch occurs. All of you are clear with the state now? Preempted? Yes, good, good. Created, right? Newly created, not ready to run. That means it is just created. It is not loaded into main memory, right? Zombie, we know that from lab, right? Process no longer exists, but it leaves a record for its parent to collect. And we know what is that record, ideally? I hope Thursday is not far way back, so you remember that from lab. What kind of record you leave? Status. We generally call it as status, or you can say one entry in the process table. Remember that? One entry in the process table will still remain for the child process, right? And after parent reads that entry, okay, that entry will be removed, right? So I hope you can recall, yes or no? What is a zombie process? Yes, right? So with this, we end this chapter number 3. I hope you are clear. Still, if there are any doubts, you read the slides and you can ask on Monday. From Monday, as I said, we'll be starting with the threads concept, and we'll try to compare process with threads. Okay? And in the lab also, we'll do thread programming. Okay. So now you can take a 5 minutes break, and at 10:05, AKG sir will start with AA class. Is that clear? At 10:05, AKG sir will start. Sure, I can explain you that. Preempted and ready to run in main memory. So basically, when a process gets preempted, right, either it can go to running state if it is getting a chance, or actually it will join the ready queue, isn't it? What do you think? In terms of queue, where that process will go after preemption? What is the answer to that? Others can also answer this. After preemption, where the process will go, in which queue? It will go in ready queue, isn't it, Ronak? It was not blocked, right? It was returning to the user mode and then it was preempted, right? So it can join the ready queue, and that's why you can see that dashed arrow. It is actually a queue transfer. Understood? All of you understood this dashed arrow? Dashed arrow, sorry. Yes, good, good. Still, if you have any queries, I can answer that in the next class, right? So you can take a 5 minutes break, 10:05, you will have AA class, right? Thank you for joining today. I'm leaving the meeting. Sure, Urjit. I'll begin with that. Don't worry. Yeah. Sure. Okay, so have a good day ahead.
Sir, hello.
Yes, Anish?
Sir, what would be the syllabus for the exams?
Yeah. So whatever I'll be covering up to the next week, that is your 4th week, right? From my portion, I have covered the introduction chapter, right? Plus this chapter, process description and control, chapter number 3 of your textbook. And I'll also cover one, not exactly complete chapter, but at least you can say half a chapter, chapter number 4, that is threads. Okay. So your syllabus will be including the threads concept. Okay.
Okay, sir.
Yeah. So whatever I'll cover in next 2 classes, up to that will be your syllabus. Okay. So you start reading these slides. I'm uploading that right now. Okay. And if you have any queries, we can resolve them in next 2 classes.